So let's take a look at the assignment that you did 2 days ago. It was called Calculating Elastic Energy, Kinetic Energy, and Gravitational Potential Energy. And we're going to go ahead on this assignment, and I'm going to actually go through the problems that you did, and you're going to be able to check your answers and maybe understand what you might have done wrong or right. When I read your answers, there was a lot of good thought in the answers that I read, but you weren't thinking through them totally accurately all the time, and that actually made them harder for you than they needed to be. Sometimes you could have written an answer very easily, and it was harder than you thought. So I'm going to kind of talk you through these. And you want to be thinking, okay, what didn't I know? What made that problem harder for me than it really had to be? All right, so the first one says, a rock is on a 10-meter high hill on Earth. It rolls to the base of the hill, as in the drawing. The mass of the rock is 2 kilograms, assuming that the hill is frictionless, so that no energy is stored as thermal energy. We got to remember that frictionless thing. It means that there's going to be no slowing down of that rock as it goes down due to friction. All right, calculate the gravitational potential energy of the rock at the top of the hill. Well, gravitational potential energy equals mass times the gravity times the height, and that is going to equal 2 kilograms times gravitational acceleration, which is 10 meters per second, and times the height, which is a 10-meter hill. All right, and when we multiply those together, we get 200. And what were the units? You could either write the units as Newton times meters. That would be fine. Usually we write this as joules. And so 200 joules is our answer for that question. 200 joules of energy will be in that rock at the top of the hill. Stored potential energy, gravitational potential energy. Now, how much gravitational potential energy does the rock have at the bottom of the hill? Well, this is not a difficult answer, actually, because at the bottom of the hill, its height is 0. All right, it's not up the hill. It's not 10 meters up the hill anymore. So if we just put 0 in there, we can see that this whole equation would end up being 0. And so there is no more gravitational potential energy in there. I'm not going to explain the answer now because I just did. So 0 joules. How much kinetic energy does the rock have on the bottom of the hill? Well, what you need to remember is that there is conservation of energy. Energy is not lost. Again, it's like money. I can give you money, but the energy is just somewhere else, or the money is just somewhere else. It's not lost. So if that gravitational potential energy became 0, well, how is it stored now? Well, the rock's going faster. It sped up as it went to the bottom of the hill. And I told you there's no friction. That means there's no slowing down for this rock as it goes down the hill, and therefore it must have 200 joules of kinetic energy at the bottom of the hill. All that potential energy became kinetic energy. All right, so that was an easier answer than a lot of you thought it was. All right, but you have to be thinking through, like you did with the pie charts, how is the energy stored? The potential energy is now stored as kinetic energy at the bottom of the hill. So now we have to use the kinetic energy equation and that kinetic energy to find the velocity of the rock at the bottom of the hill. Kinetic energy equals 1/2 mass times velocity squared. And if you want to write an exponent, you write in Google Docs, you highlight it, you write control period, and it will be an exponent, and I'm going to write control period again to make my letters big again. So 1/2 mv squared. Now, let's substitute in there, or actually I'm going to rearrange that equation. So kinetic energy equals 1/2 mv squared. I'm going to end this video right now. I am going to solve this equation in the next video, but they only give me 5 minutes to talk. And so I'm going to end the video. I'm going to come back to this problem in the next video.